In this lecture, we are going to learn about what we call the variation of parameters method. So variation of parameters method. Variation of parameters. So why we use the variation of parameters? We use the variation of parameters to find a particular solution, what we normally call YP of this differential equation, second order a linear differential equation in standard form. So qx y equal fx. So that's the goal. So we use the variation of parameters method to find the particular solution of a second order non-homogeneous differential equation. So we know that we already discussed what we call the undetermined coefficient method. So undetermined coefficient method. Undetermined coefficient method. We know that it only works for three cases. Only works for when fx equals these three cases. What are three cases? The fx function can be a something times e to the at type, or a cosine beta t plus b sine beta t. Actually, here I assume that the independent variable is t, but it can be t or x depending on the function. And the third case is a t to the n plus b t to the n minus 1, like that, a polynomial. So those are the three cases the undetermined coefficient method works. So it's the exponential function, sine cosine function, and the polynomial. So now the problem is, if you have a problem like this, so this method, so undetermined coefficient method, does not work for a problem like this, for a problem such as let's say we have y double prime plus px, y prime plus qx, y equal, let's say, tan x. So if you have a problem like that, it doesn't work. So what is the reason why it doesn't work for this kind of problem? So you can see the reason is, you can say if you take the derivatives, so we can start with tan x, and then we can repeatedly take derivatives. So derivative of tan x is secant squared x, and then if you take the derivative of secant squared by the chain rule, it is 2 secant squared x tan x. And then if you take one more derivative, you're gonna say 4 secant squared x tan x, actually tan squared x, plus you have more term. We have 2 secant 4th power x. So you're gonna keep going like that. You can see all of those terms are different. So that means you can see that the derivative, you always get a like different derivative every time. That's one reason. And then also you can see that you cannot write a derivative as a linear combination of previous ones. So that's a major problem. So you can write a derivative as a linear combination of the previous one, but that works in the previous situation. When you look at the undetermined coefficient method, you can see in those three cases you can write the derivative as a linear combination of the previous ones, but that doesn't work anymore. So that means we need a new technique. So need a new technique. The new technique is what we call the variation of parameters. So let's talk about that now. So we have ax, y double prime plus bx y prime plus cx y equal fx, let's say dx, like that. So what we're going to do, the first step is we're going to find two linearly independent solutions of the homogeneous equation. What we can do, we only consider the homogeneous part of this equation and find two linearly independent solutions. That's the first step. So find two linearly independent find two linearly independent solutions of the homogeneous equation. Homogeneous equation ax y double prime plus bx y prime plus cx y equals 0. And you can see that when you look at this differential equation, this can be several different types. For example, this can be constant coefficient, because ax, bx, cx can be constants. This can be constant coefficient. Oh, this can even be a Cauchy-Euler type. Cauchy-Euler. So it can be one of those types. Now what we can do, and even you can use the reduction order method to find the second solution of this one. If you know one solution, so it can be reduction of order also. So you can use any of those techniques to find two solutions. After we get the two solutions, now what we're going to do, so let them be a y1 and y2. So those are the two solutions, y1 and y2. Now what we're going to do, the second one, we're going to write the original differential equation in the standard form by dividing by ax. So divide by ax. So we can divide the original equation by ax. So then we can write this new equation like this. So we can say y double prime plus px y prime. Here px means bx over ax plus, and then qx y equal fx. Here fx is dx over ax. So this is the equation we're gonna consider. Now the interesting thing is we're gonna assume a special format of the solution. So we're gonna assume that. So assume a solution, the particular solution yp of the form, let's say yp, we can write this yp in this form. It is u1 times y1 plus u2 times y2. So the y1, y2 are the solutions that you found earlier. So these are the two solutions. We have y1 and y2. Those are two solutions. So what we can do, we can use those two solutions to write the yp. It's quite interesting. So we can assume that the solution is of this form, y1, u1, y1, u2, y2, where u1, u2 are the unknown that you need to find. So you can say where u1 and u2 are unknown functions to be determined. So the goal is to find those two functions. Yeah. So we're gonna find y1 and y2. So after you find y1, y2, and then we can come back and plug in there, and you're gonna get the solution. So let's see how we're gonna do that. So what we normally do, we're gonna, like, as we did in the undetermined coefficient method and earlier, we can take the derivative and plug in there and try to find u1 and u2. So let's see how we can do that part. So taking derivatives, So we can write yp prime. So use the product rule. So you can write this one as u1 prime y1 plus u1 y1 prime. Similarly, you have u2 prime y2 plus u2 y2 prime. So we can isolate some of the terms which have the derivatives of the unknown function. We can isolate them. So we can write this one as u1 prime y1 and also u2 prime y2. So those two have derivatives of the unknown function, and write the rest. So we have u1 y1 prime plus u2 y2 prime. Now we're gonna make a assumption. So we're gonna, because you need to find u1 and u2, so that means you need to create two equations for that. So one equation is, we're gonna make this term, we're gonna assume that that's assumption, we set this part equal to 0. So you can do that because you need to create two equations and there are two functions, so we can make this one. So that's the first one. So we're gonna set, so we're gonna say set u1 prime y1 plus u2 prime y2 equal to 0. So you're going to set that. So that is the first equation that we're going to use to solve for u1 and u2. That's the first equation. I'm going to call equation number 1. Now, after this assumption, your yp prime simply becomes only the last two. This become u1 y1 prime plus u2 y2 prime. Now what we're going to do, we're going to take the derivative of this one. So if you take the derivative of this one, it is u yp double prime. Again, use the product rule. So if you use the product rule, u1 prime y1 prime plus u1 y1 double prime plus, similarly, u2 prime y2 prime plus u2 y2 double prime. Now what we can do, we're going to substitute these in the equation. So we're going to substitute this in the non-homogeneous equation. So substitute into the non-homogeneous equation. So we're going to substitute into the non-homogeneous equation. So we can do that. So let's see what we get. So you're going to get, so our equation is y double prime plus px y prime plus qx y equal fx. Since we know that the yp is a solution, we can substitute. So we're going to substitute. So then you're going to get u1 prime y1 prime plus u1 y1 double prime plus u2 prime y2 prime u2 y2 double prime. That's the first term. Then plus px times the first derivative. So it is u1 y1 prime plus u2 y2 prime, and then the qx term, qx times the original one, it is y1 u1 y1 plus u2 y2. This everything simply equals to fx because it's a solution. Now what we can do, we can isolate certain kind of terms. You're going to first look at the terms with u1 in there. So we have this which has a u1, and then this has a u1, this has a u1. So we're going to isolate those terms. So we're going to say u1 times and get the rest. So what we have, you can write this one as y1 double prime plus, from the next one, px y1 prime plus qx y1. Similarly, you can see these terms have u2. this one has a u2, this one has a u2, this one has a u2. So we can isolate that also. So let's say plus u2 times, we have a similar term. So it is y2 double prime plus px y2 prime plus qx y2. You can see, and then you have just few more terms left. So you can see that you have what is left. So you only have this one and that one left, and on the other side you have fx left. So let's write them. So we have u1 prime y1 prime plus u2 prime y2 prime equal fx. So those are the terms that we have now. So now what we can do, we notice something. We see that since y1 is a solution, this term is simply equal to 0. Similarly, since y2 is a solution, this term is also equals to 0. So those two terms gonna go away. So you only end up having u1 prime y1 prime plus u2 prime y2 prime equal fx. So that's the second equation we're going to use. That's the second equation we're going to use. That's the equation number 2. Now what we can do, we can use those two equations to solve for u1 and u2. So the third step, solve the two equations. Solve the two equations to find u1 and u2. So what are the two equations again? So the one equation is u1 prime y1 plus u2 prime y2 equals 0. That's one. The other one is u1 prime y1 prime. See the format. And the u2 prime y2 prime equal fx. So the easy way to remember is, if you look at the column wise, u1 prime, and then y1 prime, and the u2 prime, y2 prime. So it's easy to remember. And that is the equation we're gonna solve to find u1 and u2. After you find u1 and u2, you go back and substitute and you get the solution. So this is the kind of solution technique, and let's see actually how we can do this part. So let's discuss that. So so what we do rest. So in the next part, what we can do, we can write 1 times, you're going to multiply equation number 1 with y1 prime. Once you do that, you're going to get u1 prime y1 prime plus u2 prime y1 prime equals 0. And then you multiply the second equation by y1 because that's the missing term. Once you do that, you can see the first terms are exactly the similar. Exactly the same. So you're going to get y2 prime y1 y2 prime equals y1 fx. Now what we can do, we're going to subtract the first one from the second one. Okay, once you subtract, you can see once you subtract, these two terms going to get cancelled out. So you simply get, you can isolate y2 prime term. So you simply get that y1 prime minus y2 y1 prime. On the other side, you have y1 fx. Now you can see that, do you notice anything? What is this term? You can see this is simply the Wronskian. So you can see this is simply the Wronskian of y1, y2. y1 comes first. So So that's a Wronskian. So because of that, then you can write this part as u2 prime, the Wronskian of y1 y2 equal y1 fx. So, and then you can say y2 prime if you divide by the Wronskian, because we know that these two solutions are linearly independent, the Wronskian not equal to 0. So everything looks great. So this is a Wronskian, but this is not equal to 0 because they are linearly independent solutions. And then what's going to happen once you divide, you're going to get that y1 fx divided by w y1 y2. Now what we do, we can integrate to get y2. So we can integrate now. So let's integrate. So by integrating, you're going to get u2, which is equal to the integral of u2 prime. That's a derivative. So once you integrate, you get the function back. So this is the integral of y1 fx over the Wronskian of y1 y2 dx. So that's the first one. Now you can see that if you switch the indexes from y1 to index from 2 to 1, you're going to get the other one because it's exact same thing. You just need to multiply by the other one. So let's do that. Let's switch the index. Then you're going to get the next one. So similarly, you're going to get u1, which is equals to y2 fx. So here, remember, this now become y2 y1 because you change the index. But what we're trying to do, just to make things easy, we're gonna switch these two. So then you have the exact same Wronskian. So let's do that. Once you switch, that means you get a negative sign because it's a determinant. So this become y2 fx, and this now become w y1 y2 because it's easy to remember. So this order matters. So be careful with that. So this order matters. Okay, good. Now you can write the formula. So that means, so therefore, the particular solution. So you can see, therefore, the particular solution yp, which is simply, so we can write, it is simply u1 y1. So it is simply u1 y1 plus u2 y2, but we can write the positive terms first. So that means we can write y2, the integral of y1 fx over w y1 y2 dx minus y1 times y2 fx over w y1 y2 dx. Unfortunately, we cannot simplify this further than that, but you can use this as a formula. So you may use this as a formula.